So, what's involved in soil formation when soils form? We know it takes time, but how does it happen? Well, we can think of soil formation as really a process of weathering some original material combined with the addition of novel biological material. And when we think of weathering, we can think of two fundamental types of weathering. We can think of physical weathering and we can think of chemical weathering. In this crude cartoon, we've got physical weathering represented, or mechanical weathering represented on the left, where we have wind, rain, heat and cold, ice, frost, all involved in the splitting of some parent material or rock into finer materials. And then we have chemical weathering. The key part of physical or mechanical weathering is that mechanical weathering typically is breaking the bedrock down into finer and finer particles, but it's not changing the actual composition of that bedrock. So, think of a sandy beach where each particle is just a really, really tiny rock. And so it's been ground down into a smaller and smaller piece, but chemically it hasn't necessarily been altered from its original form. It's just a small piece of that original rock. So physical weathering is critically important and certainly part of soil formation. It also can take a long time in terms of um, how long it takes for a rock to get broken down into really small, alluvium. Um, so this is only one type of weathering, though. So we have, disintegration into minerals or physical breakdown of this material, and of course it does vary by type of original bedrock, how quickly that physical breakdown can occur. And then we have decomposition by chemical breakdown or chemical weathering, which can be much more rapid, but it's just a different type of change. In chemical weathering, we can actually change the composition of that original parent material into something novel, and that's pretty important. So types of chemical weathering reactions that you might be familiar with from chemistry class are things like hydration, hydrolysis, dissolution or carbonation. That's a really common one that we think of with calcium carbonate, for example. There can be oxidation reduction reactions, of course. These are often oxidation reduction reactions. We have complexation. And then we'll also talk about ion exchange, which is just another form of chemical interaction in the soil that's critically important for nutrient relations. Chemical weathering releases phosphorus for sure. This is maybe one of the more important functional elements of chemical weathering for plant growth. Of course, when ecosystems are young, and when they're volcanically young, when you're dealing with raw parent material, that tends to be when you have the highest amount of phosphorus in the system. And then because phosphorus is really kind of a single direction cycle, you start with a large amount in the bedrock and then it weathers away as the system ages. Along the way, you need chemical weathering to take phosphorus that's bound in rock and make it biologically available. And so you have some chemical weathering that releases phosphorus. It becomes organically bound or organically useful for an amount of time. And then over time, all phosphorus in a system may degrade and disappear. And there are some classic examples of that. Especially in the Hawaiian Islands, for example. Okay, so here we go. Here are primary and secondary minerals, and they're arranged in terms of their resistance to weathering. So we have our least resistant and our most resistant. So you have some minerals like gypsum and calcite, dolomite, olivine. These are things that are that they weather very quickly. They're very easy to weather. And then you have other minerals, including some clays, quartz, for example, which tends to linger for a long time, that are very resistant to weathering. And so Because of this, this will determine the makeup of your soils later on in the soil's evolution through time.